So, hello and welcome to the DV Digest. My name is Brody, and this is your monthly digest of insight from design verification leaders. Now, today on the podcast, we have Surinder Sood. Surinder is a formal verification expert who's currently working at Arm, and he's also a researcher at Manchester University. Surinder has pioneered research into a technique called compositional reasoning. This is part of the picture that he sees as the move towards full chip validation. In this conversation, we talk about why he believes simulation will be replaced entirely by formal proof and the roadblocks there are to getting there. We also talk about what engineers can do if their formal skills aren't quite up to scratch. And I think it's a super insightful conversation. Really enjoyed speaking to Surinder, and I hope you enjoy watching. Surinder, welcome to the podcast. When we spoke previously, you said that you're pretty confident that formal verification is going to replace simulation almost entirely. Um, can you tell me why you think that?
That's a very good question. Uh, First of all, I would like to give a brief, know-how on what is formal verification. Basically, it uses mathematical proofs to exhaustively check that a design satisfies its specification, which is usually expressed in assertions, and it basically doesn't rely on the test vectors like simulation, but instead it checks all possible input combinations within defined bounds. Now, as of date, there are instances where formal has the capability to 100% replace simulation, typically being verifying, control logic correctness like arbiters, FSMs, or handshake protocols, safety liveness assertions, security properties like information flow or privilege checks, deadlock or live lock freedom, or credit-based protocols, or any compliance protocol checks like AMBA, AXI, CHAI, and stuff like that. Having said that, simulation remains still essential for the domains like data path verification, performance verification, analog or mixed signal co-simulation, and then you can think of like long sequential scenarios like boot sequences where, as of date, formal has not been applied. Now, the question is, is there any chance that to these things, formal can replace simulation? The research has begun, and within near future, you will see that the domains which are currently not being touched by formal will eventually be touched. Now, how it can replace simulation in its entirety? Only with the following key advancements, like you can think of compositional reasonings. Compositional reasoning is a technique using which we can verify larger systems. And these are the things which I have initially started as a part of my research, and I am moving at a a good pace when I integrate smaller systems and create a bigger systems and verify that bigger system using these compositional reasoning techniques. If we can advance in better abstraction techniques for data paths and environments, definitely simulation can be replaced in data path verification by formal. And high level property inference from natural specs or code, that is also a piece of my research I'm moving in, using also integrating in it with various AI and ML techniques. So if we can have high level property inference, which is clubbed with various AI and ML techniques for automatic invariant generation or proof strategies, I think bigger systems can be verified. And finally, last but not least, the use of faster solvers that scale the hardware evolution. So if we have that, if we can facilitate that, then definitely formal can replace simulation. So these five things which are currently lie in the research domain, and I have picked one as a part of my research, which is the first one, which is compositional reasoning. And other ones definitely people like me are researching all over the world. And if we are able to address either of this, either one of these at least, then formal will be at the forefront of replacing simulation and in its entirety.
Okay. Interesting. I think there's going to be a lot of people that won't like to hear that, first and foremost. um, so, can you talk to us a bit about where the research is at the moment? So, you sent me one of these papers that was based on
Yeah,
a contract-based strategy.
yeah.
Can you talk to us a bit about that paper, outline in its most basic form what it's doing, and talk to us about where the research is going to go next?
Right, sure. Uh, the paper which I first authored couple of years back, so that was, meant for verification of real-time systems using formal techniques, in which, we had written, we have proposed a technique using which, we can verify a real-time system, which is an integration of basically it was a hybrid system, and it was an integration of a digital system and a continuous system. And we use the notion of contracts to define the behavior of those systems. And the idea was at the primitive level, or at the discrete level, at the basic level, where an individual digital system and individual continuous system, so that is verified. And then the contracts are composed in such a manner that when these two systems are integrated together to define a hybrid system, which in our world we also call them cyber physical systems. So if we can verify such cyber physical systems using those formal properties which are written at the primitive level, when digital and continuous systems were verified individually, so such a composition was the technique to verify a combined cyber physical system. So that idea, was coined at that time, couple of years back. Now, when I look forward, look at the stage where I'm right now, we have derived a lot of stuff from that idea. And using that technique, we have been in a position to write, compositional properties to verify system on chips. So which I prototyped while I was working for Intel. And similar approach has been deployed in formally verifying, bigger systems when we verify system memory management unit while in ARM. So this compositional technique, when used in a hybrid formal way, so it facilitates the verification of system on chips. But when it is verified fully formally, so it facilitates the verification of scaled up systems when we integrate smaller design and create a bigger design. When I work for the verification of system memory management unit designs.
What are the roadblocks? I know you mentioned some of them initially to do with the hardware and the processing power required to presumably run these models. What are the roadblocks to getting to a point where it becomes industrially used to have a whole chip formally verified?
So as I said that as the design scales in the complexity, so there is a known problem to anyone who is in the formal domain or who is in the verification domain. The problem is called state space explosion, and formal suffers from exponential complexity with increasing design size, especially the sequential depth. A few hundred flip-flops or the deeper pipelines, can overwhelm such formal solvers. Abstractions, cut points, or bounded depth, so they are definitely needed in most of the cases, and this limits the completeness. So one reason is a state space explosion, and second is the data path complexity, because as of date, formal is not well suited to verify complex arithmetic units like floating point units or vector units, behavioral correctness under high level software workloads, and things that depend on the huge numerical ranges. Unless they're abstracted, it is very difficult to verify such piece of logic using formal techniques. And when we have the system which defines or which integrates a lot of subsystems like peripheral subsystem or memory subsystem or CPU subsystem or interconnect. Uh, so when we integrate such systems and define a complete system on chip, formal actually dies down. It is not capable to verify such heavy piece of logic. And In these so the solution is we can deploy, compositional verification techniques in the formal world. So that is in research, as I said. But otherwise, simulation is still essential to, verify, like boot operating systems or firmware on the RTL, or run test suite or benchmarks or applications, or we can want to integrate analog or mixed signal components. So when we want to do such system level validation, I think as of date formal is not the favorable one. And finally, when we do the performance and power validation of such systems, formal doesn't stimulate time or energy behavior as of date, and the current tools which are available in the market doesn't facilitate that. Secondly, latency, throughput, and performance counters need runtime analysis, and but formal is a static verification technique and doesn't verify or doesn't facilitate runtime analysis while doing power and performance validation.
Okay, interesting. Then, uh, why are you confident then, as we said in the the sort of clickbait intro, why are you confident that tools and solvers will get to the point in fairly short order that they can overcome these challenges?
Because research is still ongoing, and these are the challenges as of date. As I said, that people are researching on those five pillars of formal, which require extensive and intensive research: compositionality, data path verification, abstraction techniques, and better solvers. So people have not stopped, and they are working on it day and night. And one such pillar which I have picked, like, it has definitely give me better ROIs, because I am able to verify intricate properties using existing formal solvers, using the notion of compositional verification. And I have applied compositional verification, as I said, on systems, but that doesn't use formal, but the properties are used in a compositional way when we deploy them at the simulation platforms. So this imbibes in me and to the entire formal community the confidence that formal will definitely give a tough competition to simulation.
So, how are you confident that the other four pillars will be solved? Because obviously, the first time I spoke to you, you sounded, I think you said you were 100% sure in the next couple of years that formal will replace simulation-based verification. Do you have visibility on those other four problems?
Uh, okay, let's handle all these things one by one. One is state space explosion. If you look back 5 years uh, in the past, uh, there were no formal tools as such. When I started learning formal verification in the year 2007-8, people are not knowing in the hardware world that there is another verification technique called formal verification, which is doing wonders. And then 5 years down the line, there were a couple of tools introduced in the market, like there was incisive formal verifier, or zero in was the tool at that time, which was introduced. And were saying that no, it's not a good solution because it's just verifying small arbiters and stuff like that, and it's just a waste of time. And people used to rely on the existing state of the art work, which were mostly reliant on the simulation techniques. And gradually, as the research picked, now if you see, like, uh, since 2019, if you see the curve, it has not just grown linearly, but has grown exponentially. When we say that the deployment of formal in the hardware world, what's the status? So that exponential growth within just 5 years so confirms the fact that formal has a deep scope and intercept and a deep impact in the verification world. Based on the past, we can definitely estimate the future, and this outcome definitely says that within next decade, simulation is going to be tough for its survival, and it will be only left for some sanity test cases execution. So this means that there are going to be very impactful or highly intelligent solvers which will handle the state space explosion problem. And there are universities who are doing extensive research in that, typically being Stanford or MIT and Cambridge in the UK. and people are like working day and night to find better solvers. Likewise, data path complexity. So data path complexity means that you cannot verify floating point units and vector units and so on and so forth. But today, if we see that in Cadence provided formal tools, so they facilitate such data path abstraction. Synopsys provided tools, they facilitate data abstraction. And Intel, in Intel also, like people had been doing data path verification using such formal tools, which were introduced a couple of years back. So this means that if you started using those tools within these 2 years, then you can definitely predict that in the next 2 years or 3 years, so this is it's going to be its use is going to be increase many folds among not just couple of companies but among different more small company or a big company in the hardware domain or in the VLSI domain. So this is how I will say data path complexity problem will be handled. System level validation, as I said, that the compositionality is the key and contracts with an old notion since 40-50 years back is going to be extensively derived and used when we are doing system level validation. And I have started and many more folks have started, and I'm sure that within next 5 years we will have more outcomes in this domain using compositional techniques. Performance and power, as we agree today that formal does not simulate time or energy behavior. uh, I agree. There is no solution as of now, and I'm not sure if there is any research done in this regard. But I'm hopeful that someone will definitely hitting this beast as well. And other than that, tooling and usability, people say that formal tools still require expertise to write strong properties. But as we know, as things get common and known to more public, more number of engineers, they eventually get easier to solve and handle. So this is how we can predict, and I'm more than 100% confident that the simulation is going to face the heat in the coming future.
I'm going to use that as a clip. I hope you know that. So, what do you think engineers should be doing right now? Do you think engineers that haven't done much formal should be moving into formal? And how should they approach that if it's not being given as a potential training opportunity at their current company?
That's a great question. And when I was working for ST Microelectronics long time back, and I was into a similar situation where I was asked if you can write properties. I said I don't know. So, but that was past. But I think it's not difficult. Uh, there are we can follow a step-by-step roadmap to learn formal verification. Even though you are not provided training, you can do it on your own. First of all, I think you need to understand any language using which we can write properties, like property specification language or system verilog assertions language. I started with PSL at that time, and PSL was a language, invented by IBM. During those days, it was also called Sugar, and but now, today in the industry, mostly SVA is used. So we need to get the conceptual grasp of SVA or PSL, and then we need to understand the temporal logic. So temporal logic means how we can effectively use constructs like always, eventually, until, stuff like that. So once we have a conceptual understanding of temporal logic, then we should have knowledge of the basic formal concepts like assume guarantee reasoning or proof depths or cover versus assert. And what do you mean by constraining? There are many resources available over the internet from where we can have understanding of these basic ingredients to formal. Once you have the knowledge of these basic concepts, then we can get hands on to to the free and open tools. For example, There is a tool called Symbiosis, which is popularly being used by the researchers and the students who are researching in this domain. And I think nowadays Cadence also provides some starter kits if we can get evaluation or partner access. Then there are some tools like from Mentor. Mentor provides some student versions uh, for their various formal tools. Maybe it's OneSpin, I don't remember exactly. So which student can download, or any engineer who has no access as of date to any of state of the art tools, so they can do their hands wet and dirty into these free or openly available tools. And there are guided courses and tutorials. You can have guided courses on do loss, or there is a Symbiosis like guided course, and there are many webinar series available over the internet. And there are many YouTube channels also, like ASIC World or Zip CPU, which you can subscribe to and have further understanding of formal verification aspects. And then once you have got all these things, then the question arises, I've got the knowledge, where to deploy this knowledge? Now, in that case, we need the design where I can deploy my, formal knowledge. So nowadays, thanks to Google, thanks to internet, and everything is available, and you can have open designs available. And for instance, like RISC-V, which is most popular nowadays. So you have many implementations of RISC-V which are available over the internet. You can download that design and start plugging in your concepts, formal concepts, onto those designs. And you can this is how you can get a consolidated knowledge of formal verification techniques. You can start with the simple designs like arbiters, or some basic control logic, some handshake protocols, some FSM, some FIFO, basic FIFO, full and empty conditions. You can quickly check. And once you have that level achieved, you can join some forums or open communities like Formal World Slack group is there, Verification Academy from Mentor or Siemens is there, Stack Overflow, Reddit. So there are a lot of open communities where you can interact, ask some basic questions or advanced questions, and increase your, formal verification knowledge.
That's a beautiful segue there, Surinder. As you know, we've recently launched the DV Discord, which is one of these communities that verification engineers can come and discuss everything that's in the podcast, but also more widely in verification. Um, I'm sure there's loads of engineers that would love to come and ask you more questions. When are you going to be in the Discord server ready to answer those questions?
So whenever question pops in, I have enabled the notifications. I'll be happy to answer.
Cool. Fantastic. Surinder, it's been an absolute pleasure. Super insightful for me, and I'm sure super insightful for a lot of other people as well. Thank you for coming on.
All right. Thank you very much.
So, thank you very much for watching. I thought that episode with Surinder was super, super insightful. As we just mentioned, we have set up a Discord server called the DV Discord. This is basically a place for verification engineers to come and talk about everything verification, discuss any projects they're working on, and that sort of thing. If you'd like to join, there's a link in the description below, and you'll need to message either myself or my fellow admin, Will Keen, on LinkedIn. All the links are below. But yeah, I really hope you enjoy it. I hopefully see you in the Discord.